Hi, everyone, and welcome to the first webinar within the GibbsCAM 14 series, introducing GibbsCAM 14 probing. Just a few housekeeping notes before we get started. In the bottom of your screen, you'll see a section for Q&A. Please use this section to ask any questions. We'll be answering your questions at the end of the presentation, and we will do our best to answer as many as we can. Any questions we aren't able to get to will be sent to an expert who will reach out to you directly. Today, you'll be learning on how the new GibbsCAM probing option helps streamline your manufacturing process and enhance automation from application engineer 5-axis Dan Arrington. Dan has had 27 years of experience in manufacturing with 18 years as a GibbsCAM user, 14 years of 5-axis experience, 3 years working for GibbsCAM as an application engineer. He has made components for every major industry: medical, power generation, aerospace, and lastly, has been certified as a manufacturing engineer since 2014. At this time, I'd like to hand it over to Dan.
Okay, thank you, Tess. Welcome, everybody. This is going to be probably about a 30-minute presentation of a new module that we are offering in GibbsCAM 14, covering probing. The intent of this is to let you guys know what probing can do, what the different options are, so that you can decide what is best for you and your application. So let's jump in. On our tool menu, you'll see a list for probing styluses that you can create. I've created a 6mm ball stylus, which is the most common used in our industry. You can define a tool holder and give it a stick out distance. So this would just be set up just as your probe is set up in your machine, and probably you would want to create a custom model of the actual tool holder. So we just have a simple little Renishaw artifact that they like to use for demonstration, and it covers everything that we're going to do today in one part. So let's jump in. By the way, this file will be available after our session. Okay, under probing, we have 3 options. Basic is exactly what it says, it's basic. So in this option, you would essentially be manually adding code to the program. So this is the same as the add G-code utility operation that we offer. You'd have to describe a cycle time, and then all of your code would be created here, and you would just type in whatever code you want here. So this would create a placeholder tile in the operation list, and then would be output in your program. This will require a post modification, so that we can look for this operation and the code that you have manually created. Okay, and we're going to go to shapes now. Shapes is the generic, and when we say generic, we mean the what is most standard in our industry, which is the Renishaw probing cycles. And if you're familiar with probing, probably 90% of the probes out there are Renishaw. And they use the Renishaw probing cycles. So as a standard, this is what we're going to support. So under shapes, we a single surface, X, Y, and Z. We can probe a rectangle pocket, a circular pocket, a rectangle boss, and a circular boss. So these are the most typical things that you're going to do with your probe. So operation 1, we're just going to probe a single surface, and that's going to be the Z-axis that we're going to probe and set. We have options for if we want to use that data to update the work offset, or if we actually want to get a measurement. And we'll get into the measurement stuff a little bit later. So for now, we're just going to set a work offset. So we're going to probe point, which is usually going to be on the top of the part somewhere. This is all geometry driven. So in order for the system to know you want to probe, you will need some type of geometry. And so in this case, we're just going to probe the top of this boss here. Okay, so let's go through what is involved. Feed rate. This is simply positioning moves prior to the execution of probing the surface. So these are protected position moves. So what we want to know is what feed rate do you want the probe to move at to get into position to probe that feature. And then you need to tell us roughly how long it will take for that to happen on the machine. An entry plane and an exit plane. Give us a value for clearance. This value is generally set within the Renishaw macros that reside on the control. So we just need to know roughly what that number is so we can accurately simulate this operation. Okay, and so what we've done is we've probed the top of the part there. So if we go and simulate this, and we're just going to step through it. And notice it took 2 hits because that's the standard. Okay, and so we give you, in the simulation, we give you a point to let you, that's where the probe made contact with the part. Just a simple probing a single surface and setting the work offset. Now what I have today is a post that we have developed for Akuma Renishaw cycles on an Akuma control. And so you can see that we do the tool change, move to the initial position, pick up the tool length, and after that move, every other move is controlled by the Renishaw subroutines. So we turn the probe on. This is a protected position move at our feed rate that we called out. This is to the move to probe the surface, and then a protected move back up to our clearance plane. Okay, so that's just one simple operation. All right, next we're going to probe the OD of a circular boss. Again, feed rate, whatever your machine is capable of. Roughly a cycle time for this operation. Entry and exit plane. And here we need a depth. Now this is an absolute Z value based on where your Z0 on the part is. We take into account the radius of the ball of the stylus. So when you say 80 thousandths, Z minus 80 thousandths, that's going to be minus 80 plus the radius of the stylus, of the ball. And again, give us a clearance value. Again, this is set in your macros that reside on the control. And what we want is a number that's very close to that for simulation purposes. We have options for 3 or 4 circle measurement. Redo that. And again, we're setting a fixture offset. Now this is important. Our X and Y 0 on this part are on the bottom left corner of the part. So when we probe this boss, we are not moving our X and Y to the center of this boss. The X and Y values of this boss will be output in the program to adjust so that the X and Y 0 are on the bottom left corner of the part. So let's step through that. Again, taking 2 hits. And return back to the center. Pretty straightforward. If you've manually programmed probe on a machine, then a lot of this code is going to look very familiar to you. All right, so again, turn the probe on, protected position move. We're going to probe a diameter. This is the diameter of the boss. This is our Z depth, and notice in our dialog page, we put in minus 80 thousandths, and we actually get this because it includes the radius of the stylus. It's a clearance value, and we're telling it to update work offset number 1. Protected position move, retract, turn the probe off, and we're done. And all these processes they follow the same flow, and for the most part, the inputs are very similar in every cycle type. Okay, so here what we want to do, we're going to imagine that this part is finished, and we want to go check this boss, or I'm sorry, this ID, to make sure it's in tolerance. So again, by geometry, so we need a circle that is the correct diameter and location of that surface. Protected position moves, feed rate, entry and exit. And here we're going to say, instead of set work fixture, we're going to say measurement. We want to measure this boss, or this bore, sorry. And here we want to cause an alarm on the machine if the bore is more than 5 thousandths undersize or more than 5 thousandths oversize. All of this still works the same, and so we could even change this if you want, just so we can. So let's say it can be -10 to +5. So let's redo that. Again, we'll go through the simulation quick. Again, what we're trying to do is replicate in simulation what's going to happen on the machine as closely as possible. So now when we post this operation, our call line to measure that bore is going to include the tolerance that we gave it. And if this feature is outside of that tolerance band, the machine is going to stop and an alarm will be brought up with a message on the screen. What's important here, again, this is going to be kind of dependent on your machine and how you have the Renishaw cycle set up. But what we have is a 15 thousandths tolerance band here. So if your machine, and again, this is going to be different every time, depending on how your control handles this. But the standard is that these have to be the same distance, okay? So if you had a feature like this bore and the tolerance is +5 minus nothing, then you would have to adjust the diameter of this piece of geometry, this circle, so that it is in the middle of that tolerance band. So now essentially you're changing it to, instead of a +5 minus nothing, it's ±2.5. Because that's how typically Renishaw cycles work. You can't give it an upper and a lower tolerance separately as a standard. So now we've measured, we've said create an alarm. If it's in tolerance, then nothing's going to happen and the program will continue on. All right, so here we're going to probe a single surface, but instead of using point, we can actually use a line or some other piece of geometry, straight geometry, to define a surface. So we're going to probe this surface in the x-axis, and we have to tell it what side we're coming from. So in this case, we're coming from the negative side of the part or the feature to probe it on the correct side. So again, absolute value for Z, and when it's posted, this number will also include the radius of the ball. And so if you use a line, so we just redo this. Notice I only selected that one line. What we will do is we will move you to the center of that line, wherever it is, and then probe at the depth that you've given us. And again, options for set work fixture or actually measure it. So when we reload this up, It's going to select that entire rectangle because they're all connected. So just understand, if you use a line, if you use anything other than a point, we're going to put you in the very center of that feature. All right, so the next operation is the exact same thing, except here we're using a point to define it. So I have a point that's on the edge of that part, which would be x0. Same parameters here. You get the same probing cycle. I'm sorry, that's a repeat. Okay, all right. Rectangular pocket. Again, a lot of this stuff works exactly the same. It's the same inputs. Really, all we need to do is tell it, give it a Z value for a location to probe. And then with rectangle pocket, we give you, the three options for measuring that pocket: X only, Y only, or X and Y. And because this is a rectangular pocket, if you choose X and Y, you're going to get two lines of code. One to tell it to measure the X, and then the next line of code will tell it to measure the Y of that feature. So we can simulate that real quick, but everybody knows what's going to happen. But what's really nice is that we give you these target points, so you know where the probe actually made contact with the part. Because a lot of times using a round tool, if you're just trying to visualize where did that ball touch that surface, you would be kind of guessing. So here we give you a nice feature that you can see exactly where you made contact. And we're going to do rectangular boss up here and do the same thing. Probe depth, the top of this feature is Z0, so we want to go 75 below that. And this boss clearance, again, is for simulation purposes only, for the most part. There are some cycles that will let you adjust that value, but typically it's set in hard value that's set in the macros that reside on the control. So when we say boss clearance, we mean from the edge of the ball, not from the center. So 25 thousandths means that the probe is going to move, is going to clear that wall by 25 thousandths plus the radius of the ball. So we are taking that into account for you. And again, we are doing our best to replicate what's going to happen on the machine in simulation, so that you can be sure that you won't have any collisions with your in any of these probing cycles. Okay, so we start off above the part, and this moves. So you can see we told it 25 thousandths, so that distance is going to be 25 thousandths. So that's our clearance. And you'll see that it's going to back up more than that. This value can be adjusted based on the values that are in your control. All right, and there we just probed that rectangular boss, and that for the most part covers all of the options for setting a work offset and or measuring a feature, a finished feature, to be sure that it's in tolerance. Now we have one more thing that we can do. And when we talk about what is generic, meaning what is standard, and custom, this go-to, we're going to get that because we didn't. Okay. All right. What we're trying to do here so I've created a target here. I'll explain this as we go, but you have to create a target first. So now we're going to create a probing operation. And let's say that we want to measure a circular pocket, and we're actually going to measure it. And we're going to say if it's undersize, go to, and this target would be placed above the tool that finished that feature. So if we're undersized, so say we gave it 5,000. So if that feature is more than 5,000 undersized, then I want you to go to this target, which will recycle the program, jump backward in the program, grab that tool that finished that feature, make the adjustments to the tool's offset, and then remachine that feature. And obviously, if it's oversized, if it's a bore, if it's a bore and it's oversized, then we can't make it smaller. This is a custom post. This will require customization of your post to fit your specific needs. It will require quite a bit of back and forth with the post department in order to get your post to do exactly what you need it to do. Because you can imagine we are actually creating jumps in your posted code, which has a lot of potential for causing crashes. So you will have to work with the post department extensively so that we can be certain that we don't cause a crash on your machine. There's a lot of danger in this. Calling up the wrong tool, or because you have the probe in the spindle now, if the jump doesn't happen, or if the jump goes to the wrong place in your program, then if you miss the tool change line and the tool initialization line, then you're essentially going to try to remachine that with the probe still in the spindle, and nobody wants that. So this is a very dangerous, or potential for danger. We offer it, and we are very cautious in how it is applied. And again, you'll have to work with the post department to get exactly the output that you need so we can be certain that there are no crashes. All right. So the next thing so that basically covers everything that is in the generic section. And again, we're focusing on Renishaw right now because that is the most common system in use today. So we're focusing this effort. We probably could apply this to some other system, but that would also require a lot of information and a lot of back and forth with the post department, so we can be certain we understand what's going to happen on your machine, so that we can properly simulate it, and so that the code is clean. Okay, so now let's go to this corners. If you look here, we talked about basic, which is basically you're typing in code, manually typing in code. We went through all the shapes, and now we're going to talk about corners. We have outside corner with angle, and single surface from corner in Z. Basically, you know, we want to take the corner of that and step in some distance that we tell it and measure the top of that surface in Z. Okay, so we'll just go to outside corner, entry, exit, feed rates, protected position, move, feed rates, clearance from the edge of the part to the closest portion of the stylus. So these values would also be from the edge of the probe, not from the center. All right, so here we basically started in the corner. We moved up 1 inch in Y and probed, and then we moved over 1 inch in X and probed. These corner cycles do not require geometry. These values are taken directly from your stock size values in the DCD. So right now, this corner would be X0, Y0. So let's say we adjust X in 200 thousandths. You can see that the toolpath moved. So these values are driven directly from the values in your DCD. And what this is meant to do is give you the ability to probe a corner of your stock prior to machining it. That's how all of these work. So you have outside corner, which would just take one hit in X, one hit in Y, figure out where that is and set your 0. Outside corner with angle. This would, again, this is going to depend on what system you have on your machine and how it works. But the idea here is that if you didn't have 90-degree stock, if for some reason your stock was cut on a 45, so we needed to measure this angled wall and this straight wall here and find that point, that intersection point. That's what's going to happen here. So when we give it an X distance, this is going to happen twice. So what's going to happen is you're going to get 2 hits. So we get the first hit and the second hit, and that's how the cycle works, so that it can take those 2 points and create a line, and then take the 2 points down here, create a line, and then intersect those lines to find that corner or that point. And again, work fixture, this is what this cycle is going to be for, is for setting your work offset. And based on your post, so for a standard FANUC post, 1 would be G54, 2 would be G55, and so on and so on. On an Akuma, this would be H1, H2, H3, and so on. I think we've covered it. I mean, there's a lot more that can be done with this module, but again, you know, probably going to be more custom, you know, specific to your machine and your application. But the generic stuff should apply across a wide range of machines and controls. So I think we're good there. I think we're going to wrap it up, and I'll hand it back over to Tess. I'll just say thank you for taking time out to join us today, and I know Tess is going to do some Q&A now, but I just wanted to say thanks for joining us today, and my contact info will be in the chat that you'll see when Tess takes over. So thank you, and I'll turn it back over to Tess.
Perfect. Thank you so much, Dan. We've had quite a bit of questions come in, so I hope you're ready to take quite a few questions.
Sure.
Get your water ready. We've seen all of your questions, so we're going to take some time to get through as many as we can. And like I've said in the beginning, if we do not get to your question, we'll have Dan reach out to you guys to answer any questions or an expert. So the first question we have, all seats of GibbsCAM supposedly have the basic probing. How do I enable it on mine? I do not have any probing tools.
I don't have an answer for that. In 14, you should see the basic option as I understand it. So that's an answer I'm going to have to get back to you on, because again, I'm an engineer. I'm not on the sales side of things, so I don't know how things get packaged together. So that's something I'll have to check and get back to you on.
Next question, in addition to an upgraded post, is there a software that needs to be added to your machine?
Yes. Okay, so let's just talk about Renishaw. When you buy a Renishaw probe, in addition to that, you would buy the Renishaw macro library that would be installed on your control. So you're going to have a whole list of subprograms that are loaded on your control, and they'll get called from these lines of code, and then they kind of jump back and forth between each other in order to do the measurements. So if we're going to talk about a Haas, all of that stuff is included there when you buy the if you buy a new machine that has the probing system on it, then all of those cycles are there already.
Great. Next question, can it be used in conjunction with machining the part for in-process inspection?
Yes, it can, and that's custom. Again, that's the where we are asking it to take a measurement and go to. So when we create these go-to targets, that's what that means. So, you know, you would have, let's say that operation 4 here is the finish operation for that feature. So I would put my go-to target above it, finish the feature, then create this operation after that to measure it, and then depending on what happens, jump back in the program. So you would have a go-to in your program, and it would jump backward to a specific line number and repeat that process, and at the same time updating the offsets in the control so that the feature will you know, be brought into tolerance when it's recut.
Great. Next question. Hi, we currently have Productivity Plus plugin for 2 machines. Can we switch over to this option also? And we'll probably be adding machines. So is that something they can switch over to?
You can switch over. I'm not sure if there will be any cost or charge to that. Again, I'm on the engineering side of things, so what I would recommend is contact your reseller and get the information from them on what it's going to take for you to switch.
Next question. When probing the nose circular boss, how did the probe know to avoid the two eyes just above and to the left and right of the nose?
So it doesn't, so this value, this boss clearance is how much. So if we made this, well, no, let's make this number bigger, okay? Then you're going to see it would run into something if it were there. So circular boss is going to, if you do 4-point for any type of circle feature, it's going to be at 0, 90, 180, and 270. If you do 3-point, you define the 3 points. So 0, 120, and minus 120. So again, you would see we'd run into that boss there. So we could adjust these numbers, make sure we don't run into anything. But if you do have a collision and you have collision checking turned on in simulation, then it'll report that collision.
Great. Does this work in multiple planes or just XY? Example being milled, turns, or 5-axis machines?
That's going to be on a case-by-case basis, but what I would say is it absolutely has the ability to do that. It would just depend on how your machine is set up, how your macro probing routines are set up, and then we would have to adjust the code so that it works properly with your machine. But yes, it is absolutely possible.
Okay. Is it possible to select which tool offsets can be corrected after the measurements? Renishaw parameters? T?
Yes.
Okay.
Again, that is what we are considering custom. So you would have to work with the post department to have it do what you want it to do for your specific application.
Great. We have just time for a couple more. How do I control the sequence after I recut the feature? I don't want to measure again.
And again, that's going to be custom. So that logic would have to be written into the post processor and then get output in your NC code, probably using a variable that gets turned on and off. So you set the variable to 1, you recut, and when you're done recutting, you set that variable back to 0, and then there are some lines of code that would read that and jump over the probing and continue on down the program. But again, that's custom, and understand that that has a lot of potential for disaster. So we want to be very certain that that the custom post processor that we give you works for you in your specific application.
Okay. What if that rectangle is running at an angle?
At this point, we cannot support that.
Okay.
Well, no, I'm sorry. That's not completely true. On a 3-axis machine, yes, we would not be able to support that. But on a 4 or 5-axis machine where I could rotate to get that rectangle in line with X and Y, then it would be possible to measure it and then interpolate those numbers to where the offset, or if you're measuring it. But on a 3-axis machine, we don't have that capability. I'm not even sure that Renishaw has that capability exactly. I mean, you could do it, but again, there would be a lot of custom stuff going on there.
All right, and last question, are points, lines, rectangles, and full circles the only valid geometry inputs? In particular, if a particular arc is a valid point, then is the point the center of the partial circle or the midpoint of the arc or midpoint of the chord?
It would be the midpoint of the geometry, the partial circle. It would be the midpoint of that.
Okay. All right. Well, I think that concludes our webinar today. As I mentioned earlier, I know a lot of questions came in and we thank you for a bunch of your questions. We will go through the questions and answer them. If you guys have any additional questions, please reach out. We also invite you to learn more about the upcoming series for the GibbsCAM 14, and you can find them all in the link that I'll post in the chat feature and register accordingly. We hope that you have a great day, and we'll speak to you guys soon.